This is your very last lesson for AP Calc in 2016, or whatever year it is for you. But anyway, we are going to do calculating volumes by using cross sections. This is a little bit different concept than measuring the areas between the curves and rotating it around an axis. This is actually using a shape cross section like these two pictures depict. One is a rectangle example, which is a cross section, and it is included across a certain area on a plane. The other one depicts a semicircle cross section. So you're actually putting infinite number of little cross sections of semicircles, rectangles. They could be, we'll do an example with a triangle and a square as well. So you will see how this kind of plays out. But this is a good depiction of what you're actually calculating when you take the volume of a region with a cross-sectional shape on top of an area. All right, your first example is the base of a solid is in the first quadrant. It is bounded by the x-axis, the y-axis, and this graph. All right, so our area is right here, and actually the area goes from 0 to 3. You can calculate that intersection point. So our x values are going from 0 to 3. These are cross sections, so those words are always in these kinds of problems to tell you that it is a cross section problem. The solid is perpendicular to the x-axis. This means that it's going to be with respect to x. Squares means that you are going to use as your integral the area of a square. So in this case, we have the volume of the integral of an area, which is a square. Okay, that's very important. A square's area is measured by s squared. So what we're going to take is the integral of s squared dx. So we're going to have to see what measures the side of that square. So let's try drawing this on our little diagram over here. This is what the squares would look like on this area in between 0 and 3 of this graph. And this is only in the first quadrant. So notice we have squares sitting here on top of this area, an infinite number of squares from 0 to 3. So you notice that the side of each of these squares is measured, and remember all four sides are equal on a square. The side is measured by your curve's equation. So S is equal to 3 minus x times e to the negative x. So what we're going to do is take that value for S, plug it into our volume equation. And again, we're going from 0 to 3 because the x-intercept of this curve is at x equals 3. So we're going from 0 to 3. 3 minus x, e to the negative x, dx. And we could put that into our calculator, and we should get this answer up here, 3.249. That is an example of a cross-section perpendicular to the x-axis, which means dx. It's a square. Notice on this, there is no pi. A square area does not have a pi in it. And because we've been doing discs and washers, many people want to throw a pi in here. And there is no pi in the area of a square. Remember that our volume equation is always the antiderivative of the area. So in this case, our area is a square, no pi's. All right, let's go to the next example where we have, and these you need to read very carefully. Read them. I have already done some of the graphs, but you need to make sure that you can make this graph on your calculator or wherever, And make sure, I'm assuming that you can already do that. It's expected that you can make the graph and find the intersection point, or actually the 0, which is at 3. So again, read these very carefully and do them step by step. This time, our region is between 0 and 3 because it's the this graph right here, 3 to the x, 3x to the 1/2 minus x to the 3/2, and the y-axis. It says cross sections of the solid, oops, and this cross section word gives you a hint that we're doing cross sections again. So volume equals the integral of area. It says perpendicular to the x-axis, so I know it's with respect to x. This time we're doing isosceles right triangles. An isosceles right triangle has the two legs equal to each other, correct? Correct. So the area of this right triangle is base times height, but the base and height are the same length. So this is the same as 1/2 base squared, or you could put 1/2 h squared, whichever one you would like. So drawing these right triangles, here is a triangle, they're standing up on top of this area. So here is another right triangle, and these are the legs of the triangle. This is your base, this is your height, but they're equal to each other. Here's another right triangle, base and height, all standing up on top of this area. And we want to calculate that volume that is created by those right triangles that are the cross sections. It says one leg is in the XY plane. That's how I know that this distance right here is the base. So the base is equal to this little cutesy equation, 3x to the 1/2 minus x to the 3/2. Next, this is our area formula. So volume equals, and remember 3 we found by finding the 0 of this equation, 0 to 3, actually 0 and 3 we found by finding the zeros. 0 to 3, 1/2 base squared dx, because that is your area formula. Let's plug this in. Now, on some of the AP questions, they ask you just to write out the integral expression, and I think I've mentioned this before in the other videos. Some of them, they ask you to find the actual answer. So you need to be prepared to do either one of these. This particular equation is simple enough that you could actually do this by hand, finding the antiderivative. So you should be able to do that. The answers you should get here are 27/8 or 3.375. Once again, there is no pi in this equation because we're not talking about circles, we're talking about triangles. All right, so this is example number 2. We have one more example using semicircles. Okay, going back to the last slide, I just want to mention, this should have a squared right here. I have it up here, but when you put these down here, make sure you don't forget that. That's also a very common mistake, to forget the squared. So you do have to have the squared on that. All right, let's go to our third example, which is the base of a solid in the first quadrant. So make sure you're doing the first quadrant. Here is your equation. It's already been graphed, but you should be able to graph it. Cross section means that we're doing cross sections perpendicular to the x-axis. That means dx. This actually goes all the way down, although our drawing doesn't show it. A semicircle with a diameter in the xy plane. So here is our semicircle. Semicircle, semicircle. So this distance up to the equation of the function is actually our diameter. So keep that in mind, that that distance up to the equation or the curve is actually diameter, not radius. Now, we're doing semicircles. A semicircle equation for area is 1/2 pi r squared. You're going to have to know all your little area formulas. So volume equals the integral of the area. This one is with respect to x. This problem says just write an expression involving an integral. So you don't actually have to find a number solution for this. Now, this graph goes from 0 to 2. So those are going to be our limits of integration, 0 to 2. And the area is 1/2 pi r squared. So let's work a little bit on our area first. Area equals 1/2 pi, and then r squared. R is equal to this equation. So we are going to take, actually r is not equal to that equation. R is equal to 1/2 of that equation, right? 1/2 of y, because we said this equation is the diameter, so we want to take 1/2 of that. So 1/2 of this y value is the 4th root of 4 minus 2x, and we need to square that. So our area equals 1/2 of pi. 1/2 squared is 1/4, and if we square a 4th root, remember we have power over root. We actually get a 1/2 or a square root function, 4 minus 2x. Remember, we don't really write the 2's in there, but that is a 2, because power over root means you have 4 minus 2x to the 1/2. So let's clean this up one more time. The area is pi over 8, and the square root of 4 minus 2x. All right, that's our area equation. We're going to put that into our volume. And let's finish this off, because we don't have to put it in our calculator and calculate. We just have to write the expression, the integral expression. Now, I could write pi over 8 on the outside of the integral or the inside, either one. And this is 4 minus 2x dx. We've already squared it. That's our area, and that should be our volume. If you did actually calculate this out, you should get 1.047. And that concludes our cross sections. We will be doing this assignment in class. So if you would like to get a head start on it, go ahead while it's fresh in your mind, since this was only a 12-minute little video. And we'll see you tomorrow.